Hello, my name is Mark Dougherty. I'm a professor in information technology at Halmstad University. And today I'm going to give a very short overview on analysis of electromagnetic emissions from IoT devices. Now, what are we talking about here? Well, what we can see here is that encryption has changed things like digital forensics. In the past, the police could find out lots of stuff by investigating the devices that you had, looking at the traffic on your network. And if you're investigating a crime, they will be able to collect lots of useful information. But this isn't really true anymore, because encryption has basically become more or less universal. Like 85% of the traffic on the internet is encrypted through virtual private networks and that kind of technology. And lots of phones have automatic encryption. Everything that you have on your phone is encrypted. And if we're looking at modern strong encryption algorithms like the Advanced Encryption System, RSA, we can't easily crack this, not without like infeasibly large amounts of computing power. But there's one weakness in all of this thinking, is that data has to be unencrypted in order to use it. So at the moment somebody is using data, we have the possibility of getting in and spying on what's going on. Now that isn't totally true, because there are some modern forms of encryption called homomorphic encryption, where you can do operations on data while it's still encrypted. But that's very much in its infancy and hasn't really become a major thing so far. So if we want to find out what somebody is doing, we think maybe they are doing something illegal or something, then one way of finding out what is going on is to look at the behaviour of the physical device. And this is what we call a side channel. So what we do is we look at something about the device, like the temperature of it, the amount of electricity it's using. And that gives us a clue as to what's going on inside the device. And what we're looking at in this research here is looking at electromagnetic emissions that are coming out of the processors. And an analogy here is that if you measure the behaviour of a vehicle, that might tell you something about the physical state of the driver or the load that's being carried. You might get some clues about what's going on inside the vehicle by looking at how it behaves externally. Now, electromagnetic radiation is, surprisingly enough, composed of electrical fields and magnetic fields. This is something that, although it's called electromagnetic radiation, lots of people seem to struggle to understand this. It's actually two different fields which work together in tandem. And you can do investigations of either the electric field or what's called the H field, the magnetic field. And most of the work that we've been doing is in the H field. It's more difficult than the electric field, but you can get more accurate information, you get more interesting things out of it. One of the main reasons it's more difficult is that you have to orient the field, the probe in different ways. With the electric field, we just come in with a probe and we can just measure it. And the probe can be in any direction. We'll get the same result. But with the H probe, we'll get a different result if we go this way compared to if we go this way or this way or any other orientation. So it's trickier to work with and requires more experimental work. So here's a target. This is what we're using in our research. It's a Raspberry Pi, which is one of those little mini computers which you can just buy for a few dollars, and you have a working PC up and running. And what we're trying to do is to work out what's going on inside this machine by bringing one of these probes up and listening around at the electromagnetic, sniffing around and seeing if we can find out what's going on. So here it is in the lab. In this case, we've got the H probe in a vertical orientation, but we could try it in horizontal orientations or diagonal, or however we like. And the idea is, suppose you might pick up a telephone from a criminal, then there's still stuff going on inside the phone, even though it's locked and you can't see what's happening. So we can get a probe in and look at the radiation that's coming off this device. Maybe we can get some idea of what's happening. And if we look in three dimensions, we find that we get some kind of sweet spot of where the signal strength of the particular frequency is maximum. So part of the research orients around like trying to find out where the best place to look at is. And as we'll come on to in a minute, this is more complicated than you might think. You might think, well, we'll just like look for the strongest signal, and it's actually a bit more complicated than that. And we get something like this. Now, we've got 4 different things going on here, different encryption schemes. And at first sight, these graphs look pretty much the same. The big peak in the middle is simply the frequency, the clock frequency of the device. You think, well, yeah, look, we haven't really found anything. If we look closely, we see some of these like side peaks on the side. These are what we call side lobes in signal processing. These represent resonances and so on within the system, and then we can begin to see small differences on the side lobes, and that's what we can exploit. So closer look, we can get these small differences, and it enables us to classify different activities in the processor. So in the context of this particular research, what we do, we start with the experimental data, we collect the data, we get these traces, and then we're going to go into the bottom half of the diagram here. We've got to process this data and actually like work out what's happening. So in this research, we're using a machine learning approach. We put the data into a deep learning neural network, and from there, we find we can classify the different types of encryption algorithm being used. So we can tell whether this data is being encrypted by a particular encryption algorithm. Now, the next step, which like we haven't really taken so far towards yet, is we want to get more. But I mean, ideally, what we'd like to is not just know what encryption algorithm is being, but maybe we can deduce the password. That would be neat. We're somewhere away from being able to do that at the moment. But look, you can't. If this was easy, then someone would have solved it already. So. We can't be so surprised that we haven't solved everything yet. But what we can see for sure is that some information leaks out through this side channel. We probably can't extract the complete raw data, at least not with the probes that we've got at the moment. But if we know something about what a processor is doing, that can be useful in itself. And that's an insight which was actually worked out largely in the Second World War, when they developed something called traffic analysis, where they realized it wasn't important to know what was in messages. If you knew how many messages there were and who they were going from and to, then you could work out how many military units there are in a particular area, what sort of units they are, whether they're moving from one place to another, and those kinds of things you could find out even though you couldn't read the messages. And it's a little bit the same thing here. Again, we take an indirect approach. We can find out like clues about what's going on, which can lead to the next stage in an investigation. Now, what we'd like to do is to automate this procedure, because at the moment this takes a lot of time in the lab, and you have to sit there and investigate, and somebody has to manually reconfigure the probes and do a lot of things. So it's a lot of handwork in the laboratory. What we'd like to do is to find the best place to look where the most information is coming out in. And one of the insights that we've beginning to understand is that where the signal is strongest isn't necessarily where most information is being leaked. And a good analogy of that is that if you're in a party there might be someone who's talking very loudly and boisterously and is very boring and not really saying anything. And maybe there's somebody else who's speaking quite quietly, but speaking about something very interesting and important. Okay, so just because the signal is loud doesn't mean that it's interesting. So what we want to do is to produce a new 3D plot where instead of it just being the amplitude of the signal, the strength of the signal, it tells us how much information is being leaked out. And to do that, what we need to do is to put together two different theories, information theory and electromagnetic theory, and create a combined theory which will tell us what's going on. Something else we'd like to do is to look at the far field. In the pictures, the probe was like really close to the device, but we could imagine listening to a device when it's like on the other side of the room. Now the signal will be a lot weaker then, but maybe we can get into interesting things around. And just in terms of resources, how is this work being done? Well, ELLIIT has decided to fund this work by financing a new assistant professor position at Halmstad. So we're in the process of appointing a new lecturer in applied electromagnetics. So that's really great, and we're really grateful that ELLIIT has decided to invest the resources into what I think is a very interesting field. And Halmstad is providing the laboratory facilities in this Halmstad Electronics Centre. So the very first picture, we saw this like really fancy building with all this like strange triangle-like things around. This is the Electromagnetic Centre. We do it in there. It makes sort of clean room where there's no electromagnetic radiation. The shielding keeps everything out, and we can when we're working with the signals, we know that there's nothing else coming from outside. And one of the nice things, really neat things about ELLIIT is it's a collaboration between different universities. And Linköping University also has an electromagnetic laboratory on campus Norrköping, and we're looking to try to run some joint projects and share some of the resources and workload, which I think is really neat. When you've got these expensive laboratory facilities, we need to try to cooperate and to make the best out of them. So that's just a very little overview about what's going on in this project. I hope you've found it interesting. Next time you pick up your telephone, you might wonder just what's leaking out from there.
Thank you, Mark. Very inspiring, very interesting, and we do the normal trick here, and here you're sitting.
Yeah.
Thank you.
Have you looked to see if there's any electromagnetic radiation coming out your telephone?
Well, can I see that? Well, it was totally new area because we've been doing plenty of stuff going from Linköping to Lund and now this. You're used to, can we steal information from far? But now we're very close up.
Yeah.
And how did you get interested in this?
Well, I got interested in this in several ways. I mean, I've done a lot of work historically in the signal processing and sensors area, but in rather different application fields.
Yeah.
And when I moved to Halmstad,
because you're quite British.
Yeah. I mean, I moved to Sweden like 25 years ago, but I moved to Halmstad like 3 years ago.
Yeah.
And I couldn't help you. There was lots of things going on. I couldn't help noticing that there was this really fancy electromagnetic laboratory, and I thought that looks fun, and I thought, and there were also some people working in digital forensics and cybercrime.
Yeah.
So I said, well, if we can maybe put together my signal processing experience with the digital forensics people, and here's a laboratory facility that seems here in Halmstad, which could be just the thing to try a project out.
The place to be.
Yeah.
So, but you started just to have your backstory. You're from Cambridge.
Yeah, I'm from Cambridge.
Yeah. But they have the university there.
Yeah. Well, I grew
I've
up
heard about it. Anyway.
Yeah. It's a quite old university, full of fuddy-duddies and like very. But I did my bachelor's there. And then I did a
in this area,
in
this field,
computer science. Yeah.
Okay. Yeah.
And then I moved to University of Leeds and actually did a PhD, which was more in the intelligent transport area. This was like doing machine learning for looking at an analysis of traffic flows in networks and that kind of thing. So that was, and then I moved to Sweden, and one of the things that I did a lot of work in was in signal processing and analysis, mainly in healthcare, looking at different data streams in healthcare. Could be stuff it with blood pressure meters, or because what I did the most in was in audio processing, so looking at sound. Sound is a really interesting thing to look at, and to look at it, you need signal processing algorithms. And it's like I mean, if you took audible sound, it's anything up to 20 kilohertz, which is like that's very slow compared to what we're talking about here, which is like 1.5 gigahertz. So it's like you need to gear up to a whole different and you get some of the same problems and you get different problems. But a lot of the knowledge is quite transferable.
But then, when I listen to you, I'm just saying, who are using this technique? Is it about criminals, or will it be about defense, military? Where do I find it?
You're going to find this. I mean, cybersecurity is always like two sides of the same coin. On the one hand, you have hackers who are trying to like do bad things on electronic devices, and then you have the police and already, I mean, the police. I mean, the digital forensics is one of the biggest departments in the police, because you can't do anything in society without using your electronic devices. So everywhere you leave this electronic footprint going all over the place. But the problem for the police is that criminals have worked this out, and so they encrypt everything. And there was a recent case where the police managed to break into this like encrypted message system that criminals were using, and they found about 500 gang members that they could prosecute, and it was a huge breakthrough. So, but the problem is, how do you get to this information out in the first place? How you've got to find a little chink in the armour where you can drive a nail through and open it up. And this is one of the potential chinks in the armour that is definitely there. It's very attractive from one perspective, which is that because it's quite difficult. And certainly, we're very difficult for an ordinary criminal to be able to make any of these measurements and investigate it. That would be impossible. You need rather specialised equipment. So from that point of view, it's a rather good channel to work in, because it will be rather difficult for them to close it.
But I mean, through ELLIIT, I realised how much collaborations there are. And we have the universities, and you have the different police units from different countries working together, I believe. But do the criminals do the same? Are they?
Well, I'm sure they do.
You know them. You're close to them.
Yeah, I mean, they don't. They don't sit still. And all kinds of spectacular things get done by criminals all the time. That's clear. But also. This, I mean, information security is really important for everybody in society, because if you can't do stuff securely on the internet, it's not really usable.
No.
You can't buy stuff, you can't interact with the government or do anything without this secure. You have to use your bank ID everywhere.
You don't have anything.
So, I mean, one of the things that goes on at the moment is whenever you sell a device, just about anything in the shops has to be CE marked. And for any electronic device, CE marking means that one of the tests that is done when it's CE marked is you look at the electromagnetic radiation that it's emitted. But the only thing that you're interested in is, will this electromagnetic radiation affect the operation of another device? So it just says there's a maximum amplitude of radiation that you're allowed to give out across this frequency range, and maximum energy, and that's it. What I would like to see is that, like, CE marking should also include a maximum amount of information flow as well as just like amplitude. The whole thing for me is that, like, the strength of the signal is really not very important anymore. Unless you put out ludicrously strong signals, then you're not going to affect any other devices anyway. And this is an old problem from a long time ago when electrical engineering wasn't very good, and you had to worry about these kind of interferences. You install a new washing machine and you find it interferes with the TV and things like this. But that doesn't really happen.
The good old days.
Yeah, but that doesn't really happen anymore. But we still have this really old-fashioned CE test. When actually what we should be looking at with lots of devices is, do they leak information?
But is that an easy thing to fix?
No, it's not. It's not so easy to fix. I mean, obviously, like, part of what we're going to be looking at in future years is countermeasures. How do we stop devices? You can either stop devices emitting this energy via side channels completely, or I think that's a bit unrealistic. That a more realistic thing is we ought to have to look at it and decide that, like, what's being emitted is benign, and we can't learn anything from what's going on. So if it's just like random chit chat, that's not a big deal. But but being able to guarantee that is quite a difficult problem from an information theory point of view.
But I mean, because as I've understood it, you can't get hold of the encrypted information because it's encrypted.
Well, it's encrypted.
So you need to go through the leakage. What can you read from?
Well, the point is that the data must be readable if you're actually using it. I mean, you can have all this data. So say this data is books, right? So you've got loads of e-books and they're all encrypted, right? Nobody knows what books you've got, right? But at some point, if you're going to read a book, then it's going to be decrypted at that point, right?
Yeah.
So if we can see what's going on in your computer at the moment you are reading the book, the idea is maybe we can find out what book you're reading.
So you can't see what book I'm reading, but what kind of information will be leaked.
Yeah, exactly. So
what could that be?
Well, I mean, more generally,
I had a Harry Potter. Okay.
Yeah, okay, but
you don't know that.
I mean, for example, at a very basic level, we could probably find out what program you are using to read the book.
Okay.
Okay. What kind of encryption you use? Is this a PDF file? Is it a text file? Is it you? And from there, we begin to dig down. Maybe we can then find out more specific things about, like, what.
How many pages?
How many pages? What version of the PDF? By certain changes in the encoding, maybe that changes the way the radiation comes off.
Yeah.
And then we can begin to narrow it down. Like, okay, there's lots of PDF books out there.
In the 80s, I remember when I was a kid, people watching on long played records by just watching. Oh, this must be.
Exactly.
Something like that.
So I mean, you can find out a little bit of information there, and what we're doing is sort of triangulating in on what is this, right?
Okay.
We can't find out just by one piece of information, but we can find out something about what version, what length, what language it's in, and all these different things.
Yeah.
And then eventually we can pinpoint that down. We've got a database of all the books that have been put out on PDF.
Yeah.
We can then say, well, the only one that this matches is this one.
I see. But you don't you have no actual data.
Not at the moment. I mean, that doesn't mean that. I'm not saying that we can't do that. I'm saying we can't do it at the moment. Of course, if we could, that would be great. The only way that we could probably do that is if we can read the exact information that's coming off the graphics card. Of the graphics, so we actually manage to reconstitute the picture that's on your screen.
But then you must be very close. Very close, and you have the device.
If we're working in what we call the near field, then you have to have the device like in the lab.
Yeah.
But a quite common situation is that you will have a device that gets captured by the police, right? And
a cell phone.
Yeah, a cell phone, right? And it's doing stuff, but because the screen is locked and everything that's going on in and out is encrypted, we have absolutely no idea what. So we can look at the encrypted going in and out over 4G or Wi-Fi or whatever, but because it's all strongly encrypted, it doesn't really tell us very much. But if we can then put our probe on, and then we can download all of this data that we get in the electromagnetic spectrum, maybe it will give us a much better picture of what's going on. I mean, we might not be able to find out anything, but we might be able to find out, for example, which social networks are being used to transmit the data, where's it going. Police work is never about. It's very, very rare in a police investigation that you just go to somewhere and get the answer. That's not how police work works. You get little clues. You get a bit of information here and a bit of information here, a bit of information. You cross-check this, and then that leads you along, and then you gradually peel away the layers, and the picture becomes clearer and clearer. And to a certain extent, you begin to eliminate things that it can't be. Eliminate things that are not true, eliminate people that are not suspects, and then gradually, and it's not necessarily evidence that you could convict somebody on, but once you've got a clear suspect, then you can go on to the next stage of doing more investigation, more detail. The problem in many police investigations is that you've got lots of suspects.
And can you get any kind of information that will help you to decrypt? Maybe,
but I mean, this is something which this has been done in what we call timing attacks. Where, if you get an encryption algorithm to encrypt some text, then the length of time that the encryption algorithm takes is slightly dependent on the data. Not very much, but slightly. So if you can send it enough data that you want to and get it to encrypt, you can then work out what the password is from the. And again, you can't work out completely the password, but you can narrow it down enough so that the amount of computational effort to then do a brute force attack on the bits that you don't know is feasible. If you
have enough information, you can do.
If it's a 128-bit password and you can manage to work out what 20 bits of the password are, then you've reduced the 2 to the power 10 is 1,000, so 2 to the power 20 is 1,000,000. So if you then only got a millionth of the work that you had to do before to do a brute force attack, and then maybe it's worth it.
If I have 5 matches right in the Premier League, I should be able to get rich.
Yeah, something like that.
I don't know if that's good.
So I mean, it's very, very rare that this kind of work you get exact information, exact picture, exact answers. What you get are clues, pointers, half information, which allows you to like move the investigation forward.
So, but what about time? Because this takes time. Oh, you have to take it to the laboratory and blah blah blah. Do your stuff, and then you know all the other information is very instant. And
this is why I want to try to like redo the whole way we think about the laboratory work, to look at trying to quickly find the sweet spot for the amount of information coming out. Whereas at the moment we've been looking at the strength of the signal. I don't think the strength of the signal is a useful metric in this context.
It's like
so basically everybody that has been doing this, such as us and a few other groups, we've basically been barking up the wrong tree. We've been doing it. We've just been not thinking the right way, and it just suddenly occurred to me that this might not be true. And that's always a really interesting concept, a really interesting thing when you realise in research. One of the most important things in research, I think, is when you sit down and you think, we've been doing this wrong, and that's the point where you've made where you've understood something, and from there you can try some new things and see if it works better.
Yeah. When we talk about encryptions, we must talk about the quantum technology.
Yep.
Because you can read, when the quantum technology is there, they will break every code there are.
Right. Okay. Is
that true?
Let's clear up one common misconception.
Yes.
There's two things.
That
you've got quantum cryptography, and you've got quantum computing. Quantum cryptography is where we're using quantum things to encrypt stuff with. Quantum cryptography is completely unbreakable, but it's not very practical to do on a large. You can do completely unbreakable cryptography on pencil and paper, but that's not using one-time pads, and that's not technically feasible either. Quantum computing is about using a quantum computer to try to crack ordinary encryption algorithms, and the answer is both yes and no. There are some encryption algorithms being used today, common use today, which would not be robust against an attack by a quantum computer. On the other hand, we are simply then entering a new arms race where we can think of other encryption algorithms which are strong and robust enough to withstand a quantum computer. The million-dollar question there is, like, we don't know, like, where we're going to. I mean, if quantum computers were readily available today, those quantum robust algorithms would be too expensive to run in your mobile phone to work.
Yeah.
But so we don't know. There's going to be a race now. Faster computation, especially miniaturized devices, versus development of quantum computer technology.
Yeah.
I can't tell you who will win that race, but
we will see.
We will see.
Yeah. And what about using quantum algorithms and technology with AI into your area with leaks?
I mean, we're already using AI. I mean, like. At the moment, the main sticking point is getting enough data from the laboratory experiments. But if you imagine if you're running a device at 1.6 gigahertz, then this is an experiment that generates an awful lot of data. Awful lot of data. Some big heavy computing machinery will be useful, yes, because to run all these huge deep learning algorithms with all those masses of data, it does take a lot of computational power.
And you use all these technology just to get. He's reading Lisa Marklund.
Yeah. That's the way it goes. But okay. I mean, that's just an example, of course. But as I say, that might you might be reading something else, which is which might give us a clue. We don't know yet just how far we can push this.
Well, thank you, Mark Dougherty. from Cambridge and also Halmstad. How's your halländska?
Ganska dåligt faktiskt, men
Well, you know they have the British football manager here, Roy Hodgson. He was-
yeah. He trained here.
yeah, Halmstad.
Yeah, and then we had Svennis from Degerfors.
Yeah, okay, you know it all. Well, thank you so much. Very inspiring, interesting. The best of luck in this very fascinating topic. And thank you all for participating and joining in. Let's see each other some other time.